rectifiers, and today we will be seeing about the semi-converter, right? Yesterday, the last class we have seen about the single phase full converter and two different conditions, not two different conditions, two different loads, R and RL. In R load, the working principle is very clear, and every set of thyristors will work from alpha to pi, and from that particular from pi to next alpha instant, there won't be any voltage and there won't be any current, and voltage and current will be in phase with each other, and the pattern waveform also resembles each other, and this is the condition of the single phase full converter with the R load. And when we include or when we introduce the inductor in the load side, so when we introduce an inductor values in the load side, then the negative voltage will start to appear across the load terminal. It is because of the reason, even after omega t is equal to pi, the same set of thyristors will be in conduction mode. When the same set of thyristor is in conduction, whatever the voltage available in the source, that will be available across the load terminal. This is the concept. So, because in any condition, if you see the circuit, it's a series one. The current is same throughout the circuit, starting from the source and through the SCR, through the load, and the current which is coming back to the source, everything is in series. So the current is same. Since there is only one circuit and there is no drop anywhere else in the circuit, whatever the source, whatever the voltage available in the source, right? So for example, when this T1 and the T2 is on, whatever the voltage available from this AC source, that will be available across the load terminal. Whether this is a positive voltage or negative voltage, it doesn't matter, because this T1 is shorted and the T2 is shorted. So this T1 and T2 does not care whether the voltage is positive or negative. And but because of the inductive nature of the load, the current lacks the input voltage, and the current is still a higher positive value. A positive value which is higher than the latching current, holding current. So the T1 and the T2 is still in short circuit condition. So whatever the voltage available in the source, the same will be available across the load terminal. So even after omega t is equal to pi, the T1 and the T2 is conducting, and the negative voltage also will appear across the load terminal. This is why a small negative part is appearing. And when the negative part starts to appear, and when you try to calculate the average, definitely when compared to the R load, for the same supply voltage and for the same firing angle, average DC voltage of the circuit with the RL load will be somewhat lesser than the average voltage of the circuit with the R load. Right? VDC for R load will be lesser than the VDC for R load, provided same supply voltage and same firing angle should be maintained. In that case, this will be the scenario. And another case, in RL load, we have seen two different cases. One thing, when your inductor value is small, and the negative the current will be lagging the input voltage for a small short duration, and the small negative voltage will appear across the load after omega t is equal to pi. And whenever the current becomes less than a holding current, the T2 and the T1 and the T2 will be turned off, and the next set of thyristors T3 and the T4 will be waiting for the triggering pulses to rectify the negative off cycle. Right? This is the scenario when your inductor value is very much less. But at the same time, when you increase your inductor value such that the current lags the voltage by a very big or very great angle, like 30 degree or 40 degree or 50 degree, something like that. Say that the current is lagging the input voltage by 50 degree, but your firing angle is just 30 degree. In that case, the current will be still positive in the loaded terminal, and the T1 and the T2 will be in on condition. But at omega t is equal to pi plus alpha, which means that 180 plus 30 degree, at 210 degree, we will be firing the thyristors T3 and T4, where the T1 and T2 is still conducting. Where the T1 and T2 is still conducting because the current is still greater than holding current. But by voltage polarity, T3 and T4 are forward biased, and we also have given the triggering pulses. In that scenario, immediately after supplying the firing pulses, T3 and T4 will come into picture. T1 and T2 will be thrown into off mode or in the cutoff mode. T3 and T4 will be active, and it will try to carry the main current. And once again, the negative voltage will be rectified, and it will be available across the load terminal. And this case is applicable whenever the firing angle is less than the load angle. Load angle is tan inverse of omega L by R, and this load angle phi depends on the combination of R and L. Right? To be very specific, if for a particular R value, if L value is very much high, then your load angle will be greater than the firing angle, and whatever the scenario that I explained will happen. And the waveform for this particular scenario we have already simulated, and once again I'm showing that particular waveform. You can check with that. So in single phase full converter, you can have R load or RL load. To be very clear, you can have RLE load also. Right, RLE load also. Right. As of now, we are dealing with RL load, and for RL load, no problem. And in RL load, we have two conditions. One where alpha is greater than the load angle, and the second one where alpha is lesser than the load angle. And for the condition where alpha is lesser than load angle, the current and voltages are displayed in your screen right now. Right? In this condition, the current will never touch the x-axis, and it will always stay in positive. It will be oscillating, but it will never touch the zero. But if you see the voltage, the load is experiencing the negative voltage also. The load is experiencing the negative voltage also. So within a cycle, or within an off cycle, or within a cycle, within this one cycle, for some duration, both voltage and current are positive. So when you multiply these two, we get the positive power. And after omega t is equal to pi, the current becomes negative, voltage becomes negative, but current stays in the positive value, and the multiplication of both are happening with respect to I'm talking with respect to the load. for this, the load is experiencing the negative voltage, but current is in the same direction. Current is always unidirectional in the rectifiers, right? Current is always unidirectional. We have to keep that in mind. Current cannot be reversed. The reason the thyristor is a unidirectional device. It cannot conduct in the opposite direction. So the current is always unidirectional, but the voltage can be bidirectional one, or it can be bipolar, right? It can be positive or it can be negative. So in this particular, in one cycle itself, we can understand current, both current and voltages are positive. Current and voltage are positive for some period where the power is also positive, and for a small amount of time, for a shorter period, current is positive but voltage is negative. So now we can consider the power is negative. It means that the power is transferred from the load side to load side to source side, right? And when you keep on increasing the negative, when you keep on increasing the inductor value, or when you keep on increasing the firing angle, the negative part, which is a negative part of the voltage, which is appearing across the load, will keep on increasing. And at one point of firing angle, example alpha greater than 90 degree. When alpha becomes greater than 90 degree, like 110 degree, 120 degree, the amount of positive voltage will be much lesser than the quantity of the negative voltage. So if you take average of the DC voltage, if you take average value for the DC voltage, you will get a negative value. But the current will stay in the positive direction. Average current value will be positive, but average current value, average voltage value will be negative. So in this condition, average power delivered will be negative. It means that finally the power is delivered from the source side to load side to source side. This will be the scenario, right? So in this condition of operation is called as inverter mode operation. Inverter mode operation in the sense it is not a DC to AC inverter, but the power is inverted. Power is transferred from load to source. So when you have an average voltage as negative, when firing angle is greater than 90 degree, then the full converter is said to have an inverter operation. Inverter in the sense, don't get confused between the DC to AC inverter. Inverter in the sense, power is inverted. Power is flowing from the load side to source side, which is unconventional because we expect power to flow from source to load. But in this condition, the reverse thing will happen, and we say that the full converter is working in inverter mode. And this inverter mode is applicable only for RL load. There is no inverter mode for R load, because even if you increase firing angle beyond 90 degree, the voltage will be always positive and voltage will never become negative, because by omega t is equal to pi, automatically the current becomes less than holding current, and the particular set of resistor will be turned off. So there is no negative voltage in R load, and there is no concept of inverter mode of operation with respect to R load. But in RL load, we have a concept called inverter mode, where the power will be transferred from load side to source side. Right. This is one important thing that we should remember. Right. And this waveform is for when alpha is less than your load angle. Right. What alpha that I have fixed previously? It is 1.66. So 1.66 is so 1.66 is 30 degree, almost 30 degree, and this your load angle is your load angle is omega L by R. Just a minute. Omega L by R to so the load angle is around 38. So obviously load angle is greater than firing angle. Sorry, I mean the firing angle is lesser than your load angle. So once again to explain this concept, let me change the firing angle from 30 degree to 60 degree. So the delay will be 3 divided by 360. Delay will be 3.33 millisecond. If the firing angle is 60 degree, so the complement pulse generator should have 13 point. So now once again I'm simulating the system to show you that when alpha is greater than load angle, the current becomes discontinuous. Current becomes discontinuous, and in the previous case you might have seen that the current is always positive. But here at you can see the current is negative between your 30 degree and the 60 degree. Between the load angle is 38 degree. So between 38 degree and 60 degree, the current is negative, and once again it is rising. And you can see that the voltage, the negative voltage is still appearing, but the current is discontinuous. That is very clear. I think the waveform is progressing. You can, I think it is visible to you, and you can easily understand when alpha is greater than load angle, current becomes discontinuous. So this is about the full converter, and from this particular, from this working principles, we can understand the full converter can be operated in two quadrants. Operated in two quadrants. So, what are the quadrants that the full converter can work? Anyone? What are all the quadrants that a full converter can work? Anyone? Which two quadrants the full converter is working? The capable of working? Hmm? One and two. Please check and let me know whether it is 1 and 2 or which is inverting, which is getting the negative value. Voltage is getting negative value, but the current is always positive. So which is V, which is I. Prasanna Kumar. Prasanna Kumar, are you available? No. Okay. Shravan Kumar. Shravan. Shravan Kumar is not present. Abhishek. Arjun. We start asking many people in legal. Prasanna Kumar, why are you joining now?
Sir, I joined, sir.
Huh?
Network issues.
Network issue. If you have joined already, then you can join immediately without my permission. Just now it is asking my permission. Prasanna Kumar, if you have joined already in the class, the system will not ask me to admit. Right? It is now, just now it is asking permission whether to admit Prasanna Kumar or not. If you have joined already in the starting, you can enter the class anytime, right? Why it took so much time for you after half an hour you are joining Prasanna Kumar? Okay, anyhow, okay. Shravan, what others? Arjun, where is Arjun? Who knows and who can explain me? Please unmute and any responsible people. Someone unmute and let me know. Explain what are the two quadrants it is working and how. No one understands in that case. Kushal,
Sir,
which two quadrants are working?
sir, how to take the coordinates?
Huh? Do you understand what is mean by quadrant first of all? Vishal, do you understand what is meant by quadrant? First of all, did you understand that?
Sir, quadrant means that the axis only, right?
Yes. So first quadrant, both voltage and
I'm not sure, sir.
I'm not sure.
I
Okay.
did not understand.
Shivapriya.
Sir,
Oh,
I guess first and
first and
fourth.
quadrant. Okay. Full converter will be can be operated in first quadrant and fourth quadrant. First quadrant in the sense you have both voltage and current in positive value, but the voltage will be negative. So first and fourth quadrant is the operating region of your full converter, right? That too full converter RL load, not R load. Full converter RL load can work in that condition. And another thing you have to understand when for the same negative voltage across the load terminal, which will bring down the average DC voltage. Right? Don't worry about RMS. If the inductive is increased on the load side, it will decrease the average output voltage across the load terminal. That we have to keep in mind when you calculate the load output voltages. Right, and so for different conditions, we have already seen the RMS and output voltages. Next circuit, which is single phase steady converter.
Sir, I have a doubt.
Yes.
Sir, in the graph, there is a small positive space.
No, I'm not getting. I'm not understanding your statement. What is that?
You're showing the voltage graph, right?
Yes.
In that, there is a small positive peak. The other one.
1 minute. Let me. Here.
Yeah, yes.
No, this is because of the sudden change in the VR, because the current is flowing, but suddenly it is stopped, right? It is suddenly stopped, and because of that, dI by dt, L into dI by dt, because of those circuit parameter, a small spike is appearing across the load terminal. That's all. Right, there is no problem with that. This is the nature, and to be very clear, we will not subject this alternating voltage to the load terminal, and we will have a capacitor. We will filter this out, and we should try to supply a pure DC for the load, right? So, and this is because of the non-idealities in the circuit. Otherwise, what we need to do here is you have to go and set all these parameters as a see, we have something called the snubber resistance, snubber capacitance. Everything is there, right? Everything. If you make this thyristor as an ideal one, then we can expect a pure waveform. But here we have given some random values of standard values of snubber resistance, snubber capacitance, and there is a because of this inductor, and when current goes to negative and the current goes to current immediately stops, there is a small positive spike across the load terminal. That's the problem. Apart from that, there is nothing to worry, and this is the natural thing, and you can observe this when you do the experiment in your lab also. Once again, maybe with the practical experiment, I can explain it to you in a better way. Right? I'll do it, no problem.
Okay, sir. And the current, why is it at zero? I mean, you have the other part also. No?
I'm not getting what is it? Oh, what is your question?
So the current, why does it have to go to zero?
Current, why it is?
Why does it go to zero? I mean, you have the other parts is T3 and T2, I guess.
The current is going to zero only, right? The current is in zero condition only. Between two off cycle, there is a small region where current is zero.
Why doesn't go there?
When it is going. Sorry, madam, this is what I have I'm trying to explain for the past half an hour. See, the current is you know the working happen of thyristor, right? The current, the thyristor will stop its conduction when current is less than holding current. Is that right?
Yes.
Okay, so here, by nature, this is the supply voltage. Supply voltage is sinusoidal, and current is also sinusoidal. Only thing it lacks voltage because of the reach zero, right? As per the sinusoidal waveform, the current will naturally reach zero, and whenever that particular value becomes less than holding current, all thyristors are stopped. Right? All thyristors, I mean the thyristors 1 and 2 is stopped, and the thyristors 3 and 4 are not yet triggered. So there is no path for the current to flow. So current is zero for that particular period. Some set of thyristors should be in active state to conduct the current, right? During this interval, no thyristor is in on condition. So where is the path for the current to flow? Okay, sir,
Yes, sir, got it.
yeah, okay, right, thank you. Okay, right, so the next circuit is your semi-converter. And as per the circuit, this is very much similar, and you can see only the changes. You have you have diodes. You have diodes on the bottom side. I mean, in each leg, the bottom switch is replaced with the diode. So let me measure the voltage once again here. So same setup, same input voltage 50 hertz and load is 100 ohm, and the firing angle is 6.6 millisecond. Right, 6.6 millisecond in the sense it is almost it's almost 120 degree. It is almost 120 degree. So I think we can change this. .33 millisecond, and this should be 13.33. It is now a 60 degree waveform, 60 degree firing angle. So I am now I am simulating the circuit. You can see the response here. See, for R load, the voltage for semi-converter and full converter does not have any change, right? This is the voltage and the current pattern for full converter with the R load, and the same voltage and the current pattern you can observe in the semi-converter with the R load condition. there is no change, right? So let me save this diagram for your reference, right? I'm trying to save this. Right, I'm just saving this waveform for the next explanation. Right, now let me introduce inductor here, right? Same inductor. So I'm introducing a very heavy inductance also here, like 100 millihenry. I'm introducing now. Now, for the previous condition and the 60 degree 3.3 I have set, right? So 3.3 divided by 20 into 360. It is 60 degree alpha. For 60 degree alpha, 230 volt RMS, I got 155 volt average DC value and 205 volt RMS value, right? Now, I have introduced an inductor in the load terminal, which is also a very high value, and now I am simulating. If it is a full converter, because of the introduction of inductor, negative voltage will appear and it will bring down the average DC value with respect to the previous one. Now, let us see how this is happening. Now, we have introduced the RL load here, but I think now we can stop this and we can observe the waveforms. You can see the average DC voltage and the RMS voltages are same. There is nothing changed here. It was 155, here it is 154, and this is 205, here also this is 205, right? Introduction of inductor does not play any role or it does not have any influence on the average output voltage and the RMS output voltage of the semiconductor. Right. But in case of full converter, definitely for the introduction of such a high value of inductor in the load side, the DC average DC output voltage might be dropped to a greater dropped by a greater value. Right. Now you can see only thing, the current is little bit smooth. Right. The current is little bit smooth, but you can see that the voltage is same pattern and there is no negative part across the load terminal. So throughout the working condition, here the voltage is also positive and the current is also positive. Always the power is also positive. The value may be varying, value may be oscillating, but like unlike your full converter, the power is not getting the negative value here. Right? The power is always positive. It means that the semiconductor can work only in the first quadrant. Semiconductor can work only in the first quadrant where where the power can be transferred only from source to load, not from the load to source, as in the case of full converter, right? But one thing we have to observe and we have to get clear. Now you see this the center point of the sorry, not the other one. See the instant 0.02, which is the end of first cycle, 20 milliseconds, right? By that time, the thyristor T3 and T4 is switched off, and the thyristor T1 and T2 are waiting for the triggering pulses at omega t is equal to 60 degree or at the next alpha. During that time, the thyristor T1 is also off and the thyristor T2 is also off, right? So in both legs, the top switches are in off condition, right? In both the legs, the top switches are We cannot say that it is an off condition, but here the voltage becomes negative, right? The voltage becomes negative, and but for the same due time instant, you see that current is still positive. Current is 1 ampere, right? But the voltage becomes 0. In the previous condition, in the previous case, if the current is positive in the sense the same set of thyristors are conducting until the next alpha. But here, in the conducting pair, one is thyristor and one is a diode. The diode is not working with respect to the current value. Diode is working with respect to the voltage across the terminal. So at omega t is equal to 2 pi or at 22 millisecond, in case, let me show the power circuit diagram. In this circuit diagram, this thyristor T1 and the D2, diode D2, will work up to omega t is equal to pi, from alpha to pi. And this thyristor T2 and the diode D1 will work from pi plus alpha to 2 pi. That's all. At 2 pi, definitely this diode D1 will be turned off because this polarity will change and positive cycle will appear. So this point, whatever I am marking now, this point becomes positive. So obviously this diode will be reverse biased. Right? So earlier the current was flowing through the thyristor T2 and the load terminal and the diode D1 and it reaches here. Now the diode D1 is by default it is turned off because of the reverse bias voltage. Thyristor T1 is still on, but the current is flowing through the circuit. So now we have to understand a few things here. So let me go to the my presentation from the I'm moving from simulation to the presentation. 1 minute. Let me draw a simple same power circuit, but 1 minute. It's a semi-converter, right? And when you have you have a thyristor and you have a diode, right? You have a thyristor and you have a diode in the bottom. This is negative rail, this is positive rail, and you have a thyristor, and here also you have a thyristor, and this is a diode. This is also a diode, and we have supply like this. We have supply like this, and we have here R load and N load. We have an RL load and we have a supply. Right now, for the positive off cycle, this thyristor D1 and the diode D2, this is D1 and this is T2, right? The current flows in the direction which I am marking now, right? It starts here and it is entering to the T1 and it flows to the load, and the D2 is forward biased because now this is positive and this is negative, right? So D2 is forward biased and it completes the path like this. This is clear. At omega t is equal to pi, the diode D2 will be automatically turned off. But the load is RL in nature. The current will be always lagging the voltage. Voltage has reached 0 at omega t is equal to pi. but the current is still positive. So the thyristor T1 is still able to conduct because the current has not become less than the holding current value. Now what happens? Now the current from D2, and now what happens here is, now the polarity of the supply voltage is changed, and now this becomes negative and this becomes positive. Since now this diode is subjected to the forward bias condition at omega t is equal to pi, right? At omega t is equal to pi, D2 is off, but similarly D1 will be in on condition. Already the thyristor T1 is on because the current is greater than holding current, and at omega t is equal to pi, D1 is turned on because of the forward bias condition. So now what happens? The current is flowing. Current is flowing. It is flowing like this. It is freewheeling. Now it is freewheeling. It is not the supply current. It is freewheeling through T1 and D1 during the time, during the interval between omega t is equal to pi to omega t is equal to pi plus alpha. During this interval, the current is freewheeling through D1, T1 and D1. That's why the current is still positive, and the current is once again, current has not reached the zero value. It has reached a zero value only at the next pi plus alpha. Current is still positive. Similarly, after then when you supply next alpha, T2 and D1 will conduct, and at omega t is equal to 2 pi, D1 will be reverse biased, and during this condition, the current will be freewheeling through the T2 and the D2. Now this will be the freewheeling part. And obviously, we should also understand the basics of the inductor. Inductor current cannot be stopped immediately. Even though the voltage becomes negative, voltage becomes zero, we should provide a freewheeling path for the inductor current to flow, and that is provided by the different combinations and different situation, right? Of the same length. First freewheeling path is provided by T1 and D1. Next freewheeling path is provided by T2 and D2, right? And when you have, I'm drawing the equivalent circuit here, current is still positive, but the voltage is negative at the same time, right? Please look at this diagram. The current is positive, but voltage is negative here, right? Why voltage, not voltage is negative? Sorry, voltage is zero, right? The reason for during this particular interval, the equivalent circuit is something like this. Your T1 and D1 are shorted, and you have an R and you have an RL. So if you see, the terminals of load are shorted through T1 and D1. So when you measure the output voltage, it is equal to zero because the load terminals are shorted through T1 and D1, and the current is freewheeling. So there is no voltage across the terminal, load terminal. That's why during the freewheeling time, the voltage across the voltage across the load terminal is zero. It is not positive, it is not negative. Voltage is always zero between omega t is equal to pi to omega t is equal to pi plus alpha. Right? That's why the negative voltage is not appearing, even though the current is positive. In case if you have two thyristors in the place of diodes, definitely the negative voltage will appear, and it becomes and you will get a reduced average voltage. This is a major difference between your semi-converter and the full converter. So depending upon the load nature, if your load is to be subjected only to the first quadrant, then we can prefer the semi-converter. The reason, instead of two thyristors, you can use diode, where you don't need any gate triggering circuit, no need to generate pulses. So certain amount of cost is also reduced, complication is also reduced. But in case if you need your load to be operated in fourth quadrant and first quadrant, you need a full converter. If your load is requiring only the first quadrant operation, it is preferable to go for semi-converter, right? This one you can understand, and the waveform that I have saved. So this is the waveform when you introduce the RL, and this is the waveform when you have only right. This is the waveform when you have only R. Right, you can see the voltage is very much similar. There is no change in the voltage. From alpha to pi, it is appearing on the next half cycle, pi plus alpha to 2 pi, it is appearing. Only changes current just because of the inductor. And the current is also, it is also becoming zero at one point of time, and it is rising. Right? That you have to understand. That's all about the semi-converter. In the next class, we will try to solve some problem with respect to single phase converters. Right. I think now you can leave. If you have any doubt, you can say. Otherwise, you can leave.